Okay. All right. So thanks, Miguel, for the introduction, and thanks to the organizers for this seminar series for the invitation. I was particularly happy about this invitation because I think discussions across different communities working on different approaches to quantum gravity are pretty important, and this is also what this talk is about. Indeed, there are communities working on different approaches to quantum gravity, string theory, asymptotic phase gravity. That is the approach that I've mostly worked on in the past years. But there are also causal dynamical triangulations, causal sets, quadratic gravity, if you want, loop quantum gravity, and probably Bohr. At the end of the day, what all of these different approaches to quantum gravity want to do is to understand what quantum gravity is, how quantum gravity looks like. And it is important to understand whether there are features that are common to these approaches, features that are different, whether some approaches are connected. So, for instance, if they would lead to similar, if two approaches would lead to the same physical predictions, then they could be regarded as different mathematical descriptions of the same physics. In general, even if all of the approaches would be different, it is quite important also to focus effort on the most promising directions to understand how to systematically test and compare these ideas. And also try to understand whether there are universal features that are common to all consistent approaches. And this would seem to be a reasonable and interesting question, but it's quite difficult to answer this question, especially because as it emerged in a recent workshop at Northeast, where different people working on different quantum gravity approaches met. Not only we work on approaches that have seem to have different features at high energies, at least, and different frameworks. But we also often disagree on the basic questions, on what are the questions we should answer, and what are the directions that we should take. And if you want a summary of what has been said at the Rodida program and the different ideas that are currently pursued and taken in the field, you could have a look at these visions in quantum gravity that is being published some months ago. But once we agree on some questions related to quantum gravity, even if not all approaches will agree on that, then it makes sense at that point to compare what's the outcome of different theories, of different ideas. And one possible way of looking at the different approaches and to compare them is by essentially generalizing the Swampland picture. And by this, what I mean is the following. So the Swampland program, even if it was born within the string community, the core idea of the Swampland program is that of understanding what are the universal principles of consistent theories of quantum gravity. In principle, independent of string theory. Although, to my understanding, to my knowledge, the Swampland conjectures have only been tested within string models. And till date, of course, they seem to work within string theory, and this is probably related to the origin of the string Lamport principle. But perhaps we can try to understand whether there are other consistent approaches, or whether this universal consistency principle only applies to string theory. And the Swampland picture can be generalized in different manners, different independent manners. One is the general idea of mapping the ultraviolet onto the infrared. So say that one has one idea, one proposal for quantum gravity. It makes sense to ask the question of what are the type of effective field theories it can lead to. And so what are the landscapes that come from different ultraviolet, possible ultraviolet completions of gravity. And if one can do that, of course, it's not easy or straightforward in all approaches, then we can try to understand using the same framework, the framework of effective field theory, whether there are universal principles or universal features of consistent theories. And in particular, whether Swampland ideas also hold in other approaches to quantum gravity, whether there is something beyond string theory inside of the landscape of consistent theories. And to be concrete, to start developing this framework, these ideas, we first need to agree on, we need a starting point. Say we need to agree on what is our definition of quantum gravity. And through this talk, we are just trying to be conservative, and by quantum gravity we mean a theory that is ultraviolet complete, that is unitary, that is stable, Lorentz invariant, causal, and at low energies, at least at low energies, it leads to a standard effective field theory where GR is the leading order term. And the gravitational effective field theory is indeed a really crucial part. I mean, at low energies, one needs to recover a gravitational effective field theory. But this seems to be already hard in some approaches, at least at the practical level. So approaches to quantum gravity that are based on a discreteness, a fundamental discreteness, have a very hard time recovering an effective field theory. And without that, as a zero step, one cannot really test Swampland ideas. So in order to test Swampland ideas, it is crucial in the first place to focus on ideas or approaches to quantum gravity that can recover a gravitational effective field theory at low energy.
Alessia, sorry, can I ask a quick question?
Yes.
So why the emphasis on having stable vacua? You mean exactly stable vacua? Why is there an emphasis on that? Is it essential for anything in particular?
I think not for this talk. It's just something that I guess one wants in a consistent theory of quantum gravity, but I will not use that in anything that I'm going to say.
Because there can be many vacua which are like, non-perturbatively unstable or even like rolling perturbatively, and they're fine.
Yes, but I guess it's good to have at least one vacuum that is stable, right?
So you like to have at least one vacuum which is stable?
Well, sorry, how do you know this? Actually, I'm not convinced that's the case. We don't know even our universe is stable. What do you mean? In fact, if evidence is, it seems like it may not be. So why do you say that's a precondition?
So that actually, you're right. I mean, it's not really something crucial. But
sorry, Alessia, the statement is that you have a quantum theory of gravity and that has at least one stable vacuum. So
I don't need that. Actually, I don't need that for the talk.
Okay.
But what I will need, I mean, sorry, actually, that is there. But so let me say that what I want is unitarity, causality, Lorentz invariance, and UV completeness, and low energy limit should be effective field theory with GR as the leading order term. Okay. And now, like, if I have to focus on approaches that at low energy connect to effective field theory, there aren't many, and asymptotic safety, however, is one of them. If you want by construction, because asymptotically safe gravity is the idea that quantum gravity is a quantum field theory, and in particular one that is UV complete, and since gravity is perturbatively non-renormalizable, such an ultraviolet completion has to be interacting. And this leads me to the first part of my talk, that is about asymptotic safety and some implications for or its interface with some of the Swampland conjectures. So asymptotic safety is nothing but a generalization of the concept of asymptotic freedom. So in a context of a pure quantum field theory, you can look at how couplings or how your theory changes with the energy scale. And as in the case of quantum chromodynamics, certain couplings can be asymptotically free, so they vanish asymptotically. And what this means is in theory space, so in the space of all possible couplings, it means that the normalization group flow attains a fixed point of the normalization group flow, which is free, is Gaussian fixed point. Couplings, of course, could also diverge, as it happens in quantum electrodynamics. But there is a third possibility, namely that screening and anti-screening effects at the level of the beta functions compensate so that at high energies the running reaches a finite but non-zero value. And this is the concept of asymptotic safety. But in this case, it means that the normalization group flow in the theory space reaches an interacting fixed point. And the idea of asymptotic safety in quantum gravity that was proposed by Weinberg in 1976 is the idea that gravity may be a quantum field theory if, and be then non-perturbatively normalizable, if the normalization group flow reaches such an interacting ultraviolet completion, where, of course, the theory is scale invariant and the beta functions vanish at non-zero values of the couplings. And the predictivity in this case is, I mean, as in we find idea of normalization is given by the number, is measured by the number of free parameters, that is the number of relevant directions of the fixed point minus one that fixes the scale. So this is just the general idea, but now why should we bother? So why this particular approach to quantum gravity is interesting, and what are some facts about that? Well, if it would work, it would be nice because it is just plain quantum field theory that also works for other interactions without gravity. And so it is by construction easily connected with the standard model with effective field theory. One can compute, there is a clear recipe to compute Wilson coefficients and all of that. But of course, one has to test this idea. And the existence of this asymptotically safe fixed point is actually strongly supported by computations from the past 30 years, essentially. And there is no mathematical proof, but there is an accumulation of evidence from different approximations, different regularization schemes, and all of that. So the community is by now thinks that the existence of the fixed point is pretty solid. But of course, that's just one bit of the picture. So one has to test whether the fixed point is still there if one includes matter, and it seems that the picture would still work with matter, and in particular with the matter content of the standard model, possibly beyond that, and that can be a combined gravity matter ultraviolet completion. The question of unitarity is less investigated compared to the existence of the fixed point. So there has been some advances in recent years that provides some evidence that asymptotic safety may be unitary, but I would say this is still far from being enough to make any claim. So I would say that the question of unitarity is still open. At the same time,
Alessia, sorry.
Yes.
Can I quickly ask, can you tell us a bit more what's the evidence for unitarity, even if it's not like a full
Yes, so it is about the computation of non-perturbative propagators and the fact that there seems to be only the graviton out from that. So if you look at the spectral function, there is only the peak associated with the massless graviton and nothing else on top of that.
So in particular, there's no ghosts. There's no. I guess that's
exactly.
the case here.
Yeah. And yes, there are essentially three independent of calculations of that. Still not enough, but this is what we can say so far. And then the scale symmetry at high energies, whenever you have a symmetry, it means that you have some additional constraints, some predictive power, and this is always nice. And I think that the appeal of asymptotic safety is in particular for phenomenology. In particular, the fact that one has these combined ultraviolet completions also means that some of the standard model parameters can be derived. And their derivations is actually compatible within systematic uncertainties with the measured value. And then on a less established ground, there is also a quite interesting, a potentially interesting relation between these scale symmetry at high energies, even if approximate, because of course one cannot start directly at the fixed point. But the near scale invariance of the fixed point could be related to the nearly scale invariance of the CMB power spectrum, which makes it a phenomenological appealing. And asymptotic safety doesn't even need to be fundamental, not necessarily. So it could be realized at a fundamental level, say if it is compatible with observations and if it is fully consistent. But if it turns out, for instance, to be compatible with observations, but not fully internal consistent. So for instance, if in the end we find out that it is not unitary, then but it is compatible with observations, then in principle it could be realized at an effective level. So in a sense, as a bridge between effective field theory and something more fundamental, for instance, string theory. And this is a scenario that has been proposed in this paper by the Alvis and other people belonging to the asymptotic safety community. So essentially, there would be, in terms of landscape, two different realizations. One where asymptotic safety is fundamental and has its own asymptotic safety landscape that comes from, with features that come from a fundamental quantum field theory description. But it would be different to the story if asymptotic safety is effective, and then it inherits some of the ideas, some of the features of the fundamental theory of quantum gravity. And in asymptotic safety, since it is a quantum field theory, so the framework is specific enough that one can ask the Swampland question. So can put constraints on the landscape on two different levels. So first, constraints on matter. So there can be certain matter contents that are compatible with an overall ultraviolet completion of gravity plus matter, and other matter contents that destroy the fixed point. So they are not compatible with, they would be in the Swampland. And this is actually a review where many of these ideas are explained. On the other hand, even thinking just of gravity, in asymptotic safety, there is a clear way of defining a landscape, in particular related to the sister, which actually turns out to be possible in asymptotic safety, and the weak gravity conjecture for black hole that actually seems to hold in asymptotic safety. So there is somehow partial compatibility with some ideas that come from the Swampland program and asymptotic safety landscape. But these are based on just calculations from normally Boston group calculations. And I see a question from Kumru.
Yes. Do you have examples of any string theory landscape which is, you say, is part of asymptotic safety landscape?
No, so the thing that I was explaining here would be the idea that the asymptotic safety landscape, if asymptotic safety is effective and not fundamental, then it would be inside of the string landscape, not vice versa. And unfortunately, I don't have any example. It's just an idea.
I'm just saying that if suppose somebody believes that the only things we really are sure of are string landscape, suppose I have that view, then do you have any example of your asymptotic safety situation which you can see sits in the overlap at least?
So what one can try different strategies, and so say if one just looked at a system that has no input from string theory, so say a standard gravitational effective field theory, and one looks for asymptotic safety within that context, you can actually practically compute what are the Wilson coefficients at low energy, and then see whether the Wilson coefficients that come from asymptotic safety have any compatibility with the constraints that come from Swampland conjectures.
No, I'm not talking about Swampland conjectures. I'm talking very simple. Like n equals to 8 supergravity. We think it exists. In string theory, we know exactly how we'll get this and so on. Is that compatible with asymptotic safety? How do you know this?
That I don't know. But so I mean, because no one has actually studied that, like whether there is an asymptotic safety in that.
So you have no examples where it overlaps with string theory. That's what you're saying, correct?
No, not in that sense. Not in that sense. So there is one thing that say we looked at, and that is P-duality invariance cosmological effective actions. And in that context, one can see that there is a fixed point, so an ultraviolet completion, also for the type of actions. And that would be one model where one can use the concept of effective asymptotic safety to extract predictions for low energy physics that have an imprint of string theory, but not more than that, unfortunately. And I see another question by Alex.
Hi, yeah, sorry if you've already addressed this point because I got disconnected for a few minutes, but I was wondering, so is the claim that this kind of UV fixed point in the field theory captures this theory up to infinitely high energies? Because if so, wouldn't you run into a problem with black holes?
So that will be the second part of the talk that will be discussed by Ivano in a bit. But so you have indeed these two realizations of asymptotic safety. So if it would be fundamental, then the claim would be that the theory holds up to infinitely high energies, and this can only be the case if the theory is consistent and compatible with observations. The second realization, effective asymptotic safety, would be that you can actually follow this type of normalization group trajectories in a regime where quantum field theory holds, in a sense. And beyond a certain energy scale, a transition scale, you enter a regime where the fundamental theory takes over. And then, I mean, you can only use asymptotic safety or effective asymptotic safety up to some energy scale.
Thank you.
And I see a question by Jose.
Yes, could you say a few more words of how you test the possibility of having the sitter in asymptotic safe gravity? I'm asking because quantum field theory in EDS is already a complicated thing, right? So what kind of methods can you use?
So that was more specifically about the de Sitter conjecture. So these constraints about the derivative of the potential, of the scalar potential over the potential itself. And in asymptotic safety, one can actually compute these Wilson coefficients for theories of gravity coupled to what you want. And test whether the constraints are satisfied. And in the case of asymptotic safety, there are regions where it is the de Sitter conjecture is satisfied and others where it is not. So both possibilities are, I mean, in that sense, asymptotic safety wouldn't be compatible with, would be compatible with either the Sitter or anti-de Sitter.
Okay, thanks.
And these indeed are based on the calculations, but can we say more that is not based on calculations and they are more based on the interface between quantum field theory of gravity and foundational principles of the Swampland program. And this is what Ivano will be talking about in the second part of the talk. So I'm going to stop sharing and then Ivano takes over.
Oh, sorry, I just had one more question.
Yes.
So you mentioned, you know, that you don't have cases with, you know, overlap with string theory in the infrared. But so I know, like, for instance, like in 40 n is equal to 8 amplitudes, there's, you know, a group of like Svi Byrne and others who show that like these amplitudes have, you know, surprising finiteness, like they're finite to like fourth order and so on. In the context of attendee string theory on a 6 torus, you know, we know at some point, you know, there should be some non-renormalizability at some loop order in these amplitudes. But wouldn't that be like one setting in which you could potentially test this asymptotic safety, you know, easier because you have all these, you know, you have better UV finiteness in these cases? So has that been looked at? And
yes, that could be a possibility. I think what I was saying is that so far we haven't found specific models where effective asymptotic safety is found, but there are several, and it's also kind of difficult to spot effective asymptotic safety, if you like. But this could be one system that one could look at.
I bring it up because, you know, the partial evidence that asymptotic safety, you know, is consistent without supersymmetry. It seems like with supersymmetry, such evidence would be stronger, and then maybe one could, you know. Anyway. Okay.
Yeah.
Thanks.
Thanks for the comment.
So I guess I'm talking now. I'm gonna share the screen, but meanwhile, I just wanted to add about the last comment that the calculational tools that are usually used in this sort of business cannot deal with supergravity, right? With unbroken local supersymmetry, if you will. There is no known way of doing that. So even though it would be very nice to just ask the question about n equal 8, for example, there is no known way of asking it even approximately in this context. That's why people haven't done it. Anyway, so I'm gonna share the screen. Can you see it? Hello?
Yes, we can
Yes,
see
I
it.
can see
Okay,
it.
sorry.
Yeah.
Sorry, I couldn't. Yeah. All right, I needed some feedback. Okay, all right. Thanks a lot for, yeah. Okay, so hi everybody again. And I wanted to join Alessia in thanking our fellow Swamp Ranger organizers for the kind invitation. So this is certainly an experimental work and an experimental talk, but now I'm hopefully going to delve into more familiar territory for many of you, even though I did see some, you know, some people in the audience that are more into, you know, the asymptotic safety community or related things. Very good. So as Alec anticipated, I'm here to do some damage with black hole physics. And so the main aim of what we did, in particular the latest work we put out recently, is to study or examine the scenario of fundamental ASQG using Swampland ideas, right? And you know, to be fair, this is not a new idea by any stretch. This is, you know, there are many arguments dating back decades that have to do, of course, with black hole physics, with topology fluctuations, with holography, of course. And these arguments have been made in various forms, papers, conference proceedings, blog posts even. But each of them, of course, has some potential loopholes. And here, one of our main aims was to put things together, refine these arguments, improve them, by really chipping away at all possible reasonable loopholes, right? And see if there is some core irreducible issue that still remains, right? We're really trying to play some sort of, swamplandish devil's advocate, if you will. And in that spirit, I think this kind of discussion is useful to both parties, right? Both to swamp rangers, to better understand where our ideas come from, what is the strength of their motivations, what are their connections, and so on, and then of course their implications for perhaps a string universality if you are on that side of the spectrum, as in my case. And also, I think it would be useful to other communities to understand, like, what are some directions to do further research to better understand these proposals for quantum gravity, to see if there are in fact some inconsistencies or issues that they have to be addressed somehow. So we will, in this part, I'm going to really go back to the roots, right? To the underlying origins of essentially all swampland ideas. And of course, the key players are going to be black holes, as Alec already anticipated. Black holes, topology change, and things like that. I will not allow myself to use holography because the holographic principle immediately kills any field theory of gravity from the get-go. So again, in the spirit of reinforcing both sides of the coin, I'm really trying to be as essential as possible. Still, we will conclude at the very least that topology change and black hole microstates don't exist in ASQG, and of course we will review the implications of this from both sides, right? Alessia will give her interpretations, and then I will to close. So what is the plan? Well,
Quick question.
Yeah, of course.
The approach in asymptotic safety is to try and go upwards of the RG flow with field theory calculations. Now we know in many cases that trying to compute loops, oftentimes you miss things like non-perturbative effects, other stuff. Could it be that black holes or topology chains in the end are there in asymptotic safety in some sort of way like that?
Well, our arguments or our refinements of existing arguments will indicate that the answer is no. Because as I was about to say, our methodology here is to be as basic and conceptual as possible, not to rely on technical calculations that could be based on uncontrollable methods and stuff like that. Because as you mentioned, doing things perturbatively is already hard enough. Imagine trying to include non-perturbative effects, right, without any protection mechanism. So, but the conceptual arguments I'm going to give, I think, tell us that the answer is no. Okay, so step 0 of the plan is to draw heavy inspiration from Jake McNamara's work, especially his thesis, which I think is a beautiful work that everybody should read. But drawing inspiration from this work, as I said, we are going to try to reinforce both sides of the story as much as possible, to reinforce swampland ideas by going back to the roots of what motivates them and whether these motivations do apply to ASQG. And also try to put ourselves in the best case scenario. For instance, suppose that we accept that there are no global symmetries. Let's just say that ASQG has no global symmetries. What's the big deal? So we will see in more detail what I mean by that. And then, of course, we will try to draw conclusions that are as unbiased as possible, that everybody can agree with. But of course, the disclaimer here is that I am not neutral in this story, right? My vote goes to a string universality, if you will. But still, in the spirit of the Swampland program, I will take off my string theorist hat and I will put on my Swamp Ranger hat, even though it's pretty hot for that. Anyway, so this is the starting point, the roots of Swampland ideas. And we tried to distill them to the core concepts. Here I'm showing some division that I like to make between the kinematic aspects and the dynamical aspects. Kinematic aspects are much more robust, much more resilient against uncontrolled calculations and so on. They rely mostly on topology and symmetries and things of that sort, when one can usually make rather exact or nevertheless robust statements. So I reiterate, you're not going to see many equations from now on. This is an intentionally conceptual work, because we believe that in this context, conceptual arguments that are very robust are better than maybe calculations that maybe one cannot fully trust. Right? So this is the spirit of this work. So here we tried to put together all these kinematic Swampland ideas in a way that makes sense, that it's not just some grocery list, right? And you see that there are two main themes going on. One is topology fluctuations of space-time, and the other is black hole physics. And the idea is that we will essentially shut down the former by concluding that it cannot happen in just a normal QFT, even of the gravitational field, and yet the latter will stay as an issue to deal with. So this blue shaded area is what remains if you remove all the connections to topology and holography. So black hole physics will be the key player in the end, but they're still, of course, related quite deeply. So why would we care about topology change in the first place? Well, of course, it's a natural idea, right? It's just the analog of what one does in non-gravitational gauge theory when summing over gauge bundles. In the case of gravity, summing over space-time manifolds, it's also, if you will, the fullest form of background independence. This was also detailed in some recent work that made this notion more precise. It's just some natural expectation, and it is confirmed by several lines of reasoning. For example, by running the same argument that... Was someone about to ask a question? Okay. So by running the same argument that that was made in the case of Yang-Mills theory, in the trivial topological sectors there can be instanton, anti-instanton pairs, and then which can then be separated. Now, using locality or cluster decomposition more precisely, this does imply in gauge theory that one has to sum over bundles. In gravity, the story is less clear because there are no local observables, but still a similar argument can be made, which is at least suggestive in some sense. Another argument is that black hole thermodynamics, black hole entropy in particular, can be derived in a direct way, macroscopic but direct, from calculations that involve different topology of spacetimes. And of course, it does follow from the holographic principle. Right? So these are suggestive ideas.
So Ivano, just
yes.
a quick question. Maybe this is getting ahead of the talk, but is it expected that, okay, black holes or whatever you want to call black holes in an asymptotically safe gravity, do they look at all like black holes in is there a firewall at the horizon or something like that? Because presumably if there wasn't some sort of, something violent at the horizon, one could, just repeat Hawking's calculation and then just, get that, the entropy scales of the area. And then the question would be, what is that?
Yeah. Exactly. So the point here is that topology summing over topologies in some effective way computes black hole entropy directly. But as you pointed out, Hawking's original calculation was sort of an indirect calculation that uses quantum fields on top of a black hole background. and then these fields see some sort of thermal bath that has some entropy, and the natural conclusion is that the black hole itself has that temperature, that entropy, and so on. So that calculation in particular still holds, as I was about to say at some point. And this, to me, leads to an irreducible problem with ASQG, something that has to be addressed. So I don't know the answer, but for now, the conclusion is that there are no black hole microstates. So what are those things that we see in effective field theory in ASQG? I think this is the question to be addressed, right? Yes. Okay, very good. So this idea of summing over topologies and so on leads eventually to the triviality of cobordism classes, right? Something that I guess most of people here are familiar with, and this has the virtue of fixing a lot of issues in the sum over topologies. It fixes problems with holography in higher dimensions higher than 3. It implements a certain gauge redundancy that in the holographic picture is essentially the idea that quantum states can be entangled, superimposed, and so on. But one has to trace over a basis instead of summing over all of them. There's a redundancy there. And this bottom line here is sort of my understanding, my interpretation of what Jake explained in some unpublished talks about how to recover this gauge redundancy of summing over topologies using cobordism triviality. And of course, cobordism triviality also fixes problems with topological symmetries by removing them, right? So everything is all nice once we allow ourselves to sum over topologies. But I mean, the idea is what does this picture entail in the context of ASQG, right? And what happens is that there is no way, at least that we understand, to make this work in field theory. So even just naively from a path integral kind of point of view, there is no way of doing this because, at the very least, there are uncountably many exotic R4s, just to name one example, right? So there is no sensible, understood way of measuring these things. And furthermore, even more highbrow conceptually, even without path integrals per se, the way we understand QFT is functorially on spacetime. It's something that takes spacetime as an input, right? Then you can change the input, but you don't get to sum over the inputs. Right? This would seem to be a radical change in structure. And this matches this folklore that is emerging that, yes, there is a redundancy in summing over topologies, but this redundancy is taken care of by physical degrees of freedom that are not QFT degrees of freedom. They are not quantum fields. They are, let's say, stringy excitations or stringy wormholes in the terminology of a recent paper by Jake, for example. So these ideas fit together, and they fit together with the conclusion that the SQG has no topology change. And indeed, if it did have it, the direct calculations of black hole entropy would make the case basically hopeless to reproduce them in a microscopic counting, because as we will see later, there shouldn't be any. Right? So all these ideas fit together, but there is still that open issue from Hawking's original calculation that I pointed out. Good. So yes.
Can I quickly ask?
Yeah.
So you could imagine that you have like you sometimes can get topology change just from singularities on a metric. For instance, you could imagine like two hyperboloids close to each other have a smooth metric, and at some point they develop a conical singularity, and that's where they hit.
Yeah.
Right?
Yeah.
So
yeah.
if just I just do the path integral over the metric field, and I'm gonna hit some singular configurations.
Yes.
What happens there is gonna be something that it's a UV thing, but you are gonna have to answer, and there could be topology change there. And once you have it at the level of like you can find passing configuration space where topology changes, it's very difficult not to have that contribute via loops.
Absolutely. This is something that we did mention in the paper, indeed. This is another argument for summing over topologies, right? Because you sort of get there by the integrating at the edge of the space of metrics in some given sector, indeed. So again, in the spirit of saying, like, is there a conceivable scenario where this is not a problem? Well, the conceivable scenario is that there is, because, as you said, this involves some UV region of the theory, which must be strongly coupled in the case of ASQG, then maybe there is some unknown mechanism, right, that suppresses these regions in the path integral infinitely so, in such a way that one can consistently sort of truncate the path integral in a space of metrics within a given topology. Again, I don't think there is any examples of this, but it is a conceivable mechanism. My point is that even if we allow all these conceivable mechanisms to take place, there are some issues that remain that the no conceivable mechanisms can remove. That is the spirit of this work. But very good question so far. Thanks a lot.
Ivano, one question just
Yes.
to follow up on this. I think I remember from there was this review by Astrid and Arthur Hebeker and others, the absolute Swampland. I remember there was a comment that they actually said that asymptotic safety may be compatible with theories with topology change, as well as with theories without topology change. So I was curious actually, so is there any work in the asymptotic safety community that deals with this? Or, I mean, from what I'm understanding from what you said, it seems there is no work or not analysis on that. But I was curious why they said that in the review.
So the works I am familiar with, to some extent, involve the suppression of things like some spacetimes with horizons, right? Whether you count it as an example of this, I wasn't counting it. I was thinking more of along the lines of what Miguel was talking about, which I don't know of any works that address that particularly. But there are works that talk about suppressing contributions of spacetimes with horizons, at least certain types of horizons that can be detected with some invariants that involve some non-local modifications of, or let's say maybe local but not standard effective field theory kind of Lagrangians. So this is the kind of works I'm familiar with, but of course, if there are other things, people can correct me.
Sorry, can I ask a question? I'm not sure if you're going to comment about this, but there was also this work that we did with Max and Rashmish, and in there, the conclusion was that if you have black hole contribution to scattering amplitude, then that in and by itself will include some higher derivative corrections to the action that will lead to like the breakdown of quantum field theory picture at some energy scale. So I would assume that that's already telling you that even just from the Lorentzian picture, if you have scattering processes that go through black hole production and evaporation, that would give you a problem with this.
Absolutely, and I was going to comment on this, and I believe your paper is quoted here multiple times. Let's see. So not quite in this slide, but in maybe next slide you will see.
Okay, sorry for jumping ahead.
No worries, but yes, all your points are absolutely relevant, and we did discuss them. So very good. Thanks for engaging. Yeah, so black holes, right? About black holes. So let's say, okay, we agree that topology change cannot happen in ASQG. What about black holes? Well, the standard, the first thing that comes to mind thinking about black holes is, in this context, is the age-old argument that global symmetries, at least continuous global symmetries, are absent, right? And here I wanted to put it back on, put it on the slide again, not because it will be particularly relevant, because as I said, we can just declare that we put ourselves in a setting where there are no global symmetries, period. Simple as that. But I wanted to put it here because it's worth refining all these arguments in a way that is more careful, right? Because the usual lore of let's make the black hole evaporate until it's very small and then it goes poof, that's not particularly robust. It is a heuristic, of course, that we can use to guide us. But my point is that this argument can be made, and multiple versions of this argument can be made without ever leaving the EFT regime, right? So the black hole can be always kept big. You start big, you shove charge in, you leave it big, you wait a little bit, and it's still big, right? As it evaporates. And there is a non-zero chance that you get just the same macro state with a different global charge that you cannot see from outside. And you can even engineer situations in which the black hole is kinematically unable to keep evaporating at all. It forms these large, reliable remnants, which are problematic for various reasons, thermodynamically mostly. So, and also all these conclusions match perfectly with the conclusions from the considerations on summing over topologies, in the sense that the absence of global symmetries is also implied by the holographic principle, and gravitational solitons also carry global charges of some type. So all these ideas fit together, and they can be phrased in a way that is consistent with EFT. This is what I wanted to say, even though this particular point will not be relevant, in the sense that we can just avoid it by saying, oh, let's consider ASQG without global symmetries. But there are, as I was saying before, there are some irreducible nuggets of black hole physics that we cannot escape from. And this is perhaps a different rephrasing of what Alec was saying. So there are aspects of black hole physics which are due to the fact that at least they appear to have microstates, in the sense that we can compute an entropy directly if we sum over topologies, or at least indirectly if we don't. And their degeneracy is super exponential, right? It grows faster than exponential in the energy. And moreover, the presence of these microstates as intermediate states in scattering amplitudes, say a 2-to-2 amplitude, for example, makes this amplitude decay very quickly. And again, here I'm referencing this paper in the context of weakly coupled UV completions, because these properties and other properties of black hole physics in the context of a weakly coupled UV completion of gravity lead us to support string universality, essentially, or the emergent string conjecture for those who are familiar with this term. But again, ASQG cannot be weakly coupled, right, parametrically, which means that those conclusions, strictly speaking, don't apply. But some conclusions do apply, right? So the usual arguments of that this density of states leads to an area law, and therefore it's incompatible with the volume scaling of a local field theory. I think there are conceivable mechanisms that could go around that, because in the UV these theories are strongly coupled. They can scale very anomalously, and maybe the effective dimension of space-time on very small scales is different or something like that. I'm not saying this is what happens. I'm saying that there are conceivable mechanisms. Yet I think it's better to phrase this issue in terms of the scaling with energy, because the super exponential scaling with energy seems impossible to realize with local quantum fields, even if their dynamics is non-local. Perhaps in some way that makes the theory still causal, even if non-local in the UE. Still, even if that were realizable, this is a more structural statement about the nature of quantum fields, right? Regardless of what the dynamics is. So I think this is perhaps a stronger way to say that quantum fields cannot account for black hole microstates. Again, this is not a new conclusion, but I would say it's perhaps a refined argument toward the same conclusion. Similarly, and perhaps even more robustly, in the case of the exponential, super exponential decay of scattering amplitudes, this immediately contradicts quantum scale invariance of an interacting fixed point, where amplitudes should scale either as power laws or constants, right, fixed by dimensional analysis. This immediately says that any ASQG realization at a fundamental level cannot have black hole microstates. This, I believe, is in the spirit of what Alec was saying. So the last bit of swampy wisdom that I wanted to list is in the same spirit of the absence of global symmetries, in the sense that it's easy to avoid, but it's still worth mentioning. And this is the idea of infinite distance limits. Infinite distance limits is a weird term, right? Because it sort of relies on this notion of distance, and it's a very complicated story. But for the sake of a more physically inclined talk, I like to phrase infinite distance limits as limits in the space of aqua space of theories, where the gravitational cutoff, the cutoff above which no effective field theory can describe physics, is much smaller than the Planck scale. Right. This is also related to the species bound, and we analyzed, and many of us studied the implications of these kinds of limits for UV completions of quantum gravity. And from the Swampland perspective, as well as the bootstrap perspective, there are several results that show that these limits cannot have field theory physics. And in fact, of course, in string theory, we have infinite towers of light species everywhere in all these limits. But there are, importantly, bottom-up, sort of agnostic arguments for why these towers should be there in these limits. In particular, I like to quote the argument by John Stout, because it relies on some universal features of these distances in using the notion of information geometry. But there are also other works that have to do with cobordism, triviality, and so on. So my point here is that unless a mechanism is found that sort of avoids the necessity of towers in infinite distance limits, of which there is no known example, the only conclusion to avoid the presence of towers is that ASQG has no infinite distance limits, except for the ones that are trivially present in any EFT, which are the compactifications. So if I go to the maximal dimension, there cannot be any infinite distance limits. That is the conclusion. And again, this is sort of easy to conceive, right? I can imagine some ASG realization where there are no infinite distance limits. I mean, in 11-dimensional M theory, there are no infinite distance limits either. So there's that. Okay, so let's go to the conclusions here, and then I will shortly give word to Alessia. Yes.
You only have a few minutes left. Just wanted to.
Yeah. It's basically done. But thank you for the reminder. So putting things together means, summing up what we learned so far by revisiting these arguments. So the point here is that both from kinematic and dynamical considerations that have roots in black hole physics, topology, fluctuations, and so on, even by being as, let's say, conservative as possible by saying, okay, let's remove all global symmetries, let's fix the topology, let's have a complete spectrum of gauge charges, let's say that there is no moduli space, for example, there are no limits to take. There are some irreducible bits that have to be dealt with, right? This is the spirit of this work. So black hole physics in particular, the existence of black hole microstates is a problem in the sense that ASQG cannot have black hole microstates because they directly conflict with quantum scale invariance of an interacting theory. So this is I would say, the factual takeaway that we can all agree on. Now I'm going to give word to Alessia first, and then I will conclude with my own perspective on the interpretation of this fact of these conclusions. Right. So, first I will.
Yes. So now I'm going to present my own perspective, my own viewpoint on what we found. So, asymptotic safe gravity is a minimal scenario for quantum gravity, and this is what makes it appealing for me. Also coupled to the fact that there are some interesting predictions and false predictions that are related to particle physics. And of course, one could think, okay, maybe they are coincidences, so could be, and one needs to investigate more on whether these predictions are stable and whether there are more that are in agreement with particle physics. And if that would be the case, so if still asymptotic safety is compatible with observations, so So if asymptotic safety is in some form realized by nature, then what are its possible consistent realizations? So one is the one that Ivano just discussed. So asymptotic safety is fundamental, but we need to deal with a different interpretation of a completely different interpretation of black hole thermodynamics. And I don't think that maybe this is the way to go, but again, this is my take on the thing. The alternative is to relax one or to get rid of one of the assumptions. And some of the assumptions that we have taken like to reach these conclusions are those that we discussed at the beginning, so Lorentz invariance and a fundamental scenario of quantum field theory and standard effective field theory, so no IR, no localities. Briefly, like on Lorentz invariance, I don't think this is a possibility to get rid of this, because Lorentz invariance would just be amplified at low energies. So this is essentially Lorentz invariance, I think, must be there. One possibility would be to look into infrared non-localities. So perhaps if asymptotic safety is consistent and fundamental, then there must be some modifications at the level of the effective field theory. And this is actually an outlook for myself. So would the infrared non-localities be consistent with all observations that we have at our disposal, and also would they screw up somehow causality or unitarity and all of that? So this honestly is an open question for me, because one would expect if you have strong infrared non-localities, you could mess up with observations, but to be honest, I did not find any systematic studies of this. So this is something I would look into. But another possibility is asymptotic safety works up to some energy scales. So certainly the normalization group flow of gravity has to follow what we see in asymptotic safety up to the regime where we can trust quantum field theory. And perhaps after that, above that, there can be a more fundamental description that takes over. And my question is how to spot it and how to see whether any effective realization of asymptotic safety is there. And this is an interesting to me and a completely open question. Okay.
Alessia, can I
yes.
ask you a question? So in
Yes.
this effective viewpoint,
Mm-hmm.
would it be possible that this asymptotic safety works until the Planck scale, but not beyond that, and then another description takes over? Or do you need that this effective asymptotic safety is valid beyond M Planck?
Not necessarily, in my opinion. So I know that, for instance, if you would embed that in a stringy scenario, one would need to have some effective asymptotic safety somewhat below the Planck scale. And this means that there should be an external input somehow in there, or some mechanism at least that allows for effective asymptotic safety at lower scales than what we would imagine.
Okay.
There is also a question by Jose, but yeah, go ahead.
If you want to finish. Otherwise, I wanted to ask very quickly about this effective asymptotic safety quantum gravity a bit more.
Mm-hmm.
At the end of the day, you will really have a UV fixed point, or you also relax the condition of having a UV fixed point? Because
so essentially, the statement there is the fixed point is there, but it does not provide the ultimate ultraviolet completion for the theory. So in a quantum field theory setting, the fixed point is there because this is what the renormalization group flow sees, but you don't necessarily reach it, but you can pass very, very close to it. And then you experience a regime where your amplitudes would be nearly flat, but then the fundamental theory takes over. And then you would have an intermediate regime of asymptotic safety. And why would that be appealing in connecting the two things? Because the fundamental theory would take care care of all of the consistency properties, unitarity, causality, black hole microstates, and all of that. But the fixed point at the same time would guarantee that you have an enhanced predictive power. So you would, if you would have effective asymptotic safety, you would still have this type of predictions for particle physics, because you would inherit the predictive power of the fixed point.
Okay, thank you.
And now I give the word to Ivano, who will give one stringy perspective on the topic.
Very good. Thanks a lot. Yeah, we had to sort of, strategize this. Yeah, so as I said when I started talking, I think these discussions, pushing these ideas to their extremes to understand, like, if there are some core elements that remain even in the best of scenarios, is worthwhile for everybody, right? It's worthwhile to clarify our ideas, no matter what our goal is. To understand that some ideas are deeper, some are more necessary, and maybe these two things are not the same, right? The holographic principle, I think, is one of the deepest ideas in theoretical physics, and yet in this approach, we completely avoided it, right? But we did need some nuggets of black hole physics, for example. And then, of course, there are connections that we try to highlight and get a clear global big picture of what's going on, regardless of any conclusions. And in particular, even if we want to settle the particular question of string universality, this is important, I would say. This would be the idea that, in particular, it would imply that what is minimal in quantum gravity is just what is dictated by strings. So I think, science is about understanding what the answer is, no matter what it is. So I think it's good to pursue this kind of directions. Now, for my personal take on it, I would conclude by the above analysis that quantum gravity, as we defined it, cannot be a QFT. Of course, this doesn't rule out this effective scenario that, as Alessia just pointed out, could be useful in practice to simplify a lot of the calculations, predictions, and so on, if it does occur, even though we don't have any examples. So in my opinion, I would say, given all the evidence that has accumulated, especially but not exclusively in weakly coupled contexts, quantum gravity is probably stringy, as we defined it. Now, of course, one can conceive changing the axioms, right? We can conceive changing quantum theory, for example. But my point here, and this is a point that I think is shared by people like David Gross, at least I tried to find a reference, but the earliest I could find was 2005. My point here is that these axioms, these principles, do give at least one example that works, right? So I don't see why we should mess with these principles. This is the idea of radical conservatism, right? Which sounds bad if you say it that way, but it's really the idea that physical principles are more important than the ingredients of the theory. Like it's okay to have a bunch more particles. It's okay to abandon QFT if it means keeping unitarity and things like that. So that would be my perspective here. And with that, I think I can speak for Alessia as well when I say thank you all for attending and for engaging with very, very nice questions. And we are still here for some further chat.